Welcome to this video lecture on scientific research in information systems, a set of lectures about the book with the same name, Scientific Research in Information Systems, published by Springer, 2021, second edition. This particular video lecture is part of a series on computational methods, one of the chapters in this book. And in this particular lecture, we will discuss examples, advantages, and challenges of computational support, augmentation, automation tools for research. For orientation, in the past video lecture, we introduced a very simple framework to distinguish different types of computational methods from support to augmentation or automation tools across different steps of the research process from generation, processing, analysis. In this lectures, I will give example for support, augmentation, or automation tools, some of which I've mentioned briefly in the previous video lecture. For computational support tool, one example that I mentioned are video conferencing tools that are increasingly being used by researchers because they allow you to carry out your interviews irrespective of the location and the time. So, for example, you can interview people about their work while not being in their office, while they are at home, outside of office hours, while you are somewhere else, etc., and so forth. Or, of course, if it's a purely digital organization, a virtual organization, you couldn't literally go to an office, right? If it's a freelancer working from home all the time anyway. So these tools allow you to record audio, they record video, and increasingly, they also support what you see on the right-hand side. They can automatically, in real time, transcribe the interview, the conversation that you're having, which is a form, if you want, in a strictly speaking form of augmentation, because it complements a human activity. It doesn't support you in transcribing. It literally does it for you while you're talking. And if you think about it, you could also then, in some of these tools, do automatic translation even of an interview. Let's say that's in German and you need it in English or the other way around. So these are tools that support researchers in this particular case in generating data. And there are also tools, software packages that people have developed specifically for researchers to support them in data analysis, but also, for example, in scientific writing, right? If you think about tools like Zotero or EndNote, these are library management tools that allow you to organize and manage your references and your readings that you might need for writing. These are computational support tools. As an example for computational augmentation, I brought a tool that was developed by the KIT, Karlsruhe Institute of Technology here in Germany. And it's a tool that augments researchers and supports them while doing a literature review. LitSonar, and you can see the link here, is a meta search tool that helps you identify relevant literature, right? So it can scan millions of documents for the presence of certain keywords, and it helps you to identify relevant related literature, but it doesn't automate that literature review for you, right? It doesn't support you either, but it augments it, right? It complements and amplifies what you're able to do. It can find more literature that you would be otherwise able to find, but you still have to read it yourself, of course, right? So what this does is it helps you with search, identification, and filtering, selection of papers, and then you have to read the papers yourself. Yeah. So I encourage you to go to litsonar.com and try it out for yourself. It's a very helpful tool if you do something like a structured or systematic literature review, for example, for Phoebus. It's very nice. As a second example, I'm giving you a tool that is not helpful for sort of like data generation. If you think about it, Litsonar helps you find and generate the papers, basically identify those papers that you then need to read. Here's a tool that helps you with interpreting data, especially interpreting text data. There's a tool called Leximancer, leximancer.com. Again, it was developed at a university, the University of Queensland, by a PhD student that was actually doing a PhD in psychology, but he was a software engineer. So for his psychology degree, he built a tool, a text mining tool, basically, that helps researchers understand and do an analysis of the content of text. And for example, in the actual PhD dissertation, what he does, he uses his tool Leximancer to go through the novel Romeo and Juliet by Shakespeare. And what this tool does, it allows you to identify those these content areas that the text is about, right? So for example, in the case of Romeo and Juliet, Leximancer would tell you, look, this is about love, it's about family, it's about a foe, it's about, a war of cousins, and all the different themes and topics that characterize what this novel is about. So what it actually does, it parses through the text algorithmically and produces concept maps, and an example is shown on the right, that allow you to explore and gain insights about the concepts and their relationships that are very prominent in the text. Now, this is an augmentation tool because it doesn't support you in reading the text, and it doesn't fully automate the analysis either. What it does, it augments your ability to interpret and analyze text by basically summarizing and abstracting text into these concepts maps that you still must interpret. You still have to analyze these concepts maps and figure out what they actually say and what they actually mean. Yeah. I'll give you one example of work that we've done with LexiMancer, and I think that shows you the augmentation capability of such tools. What we've done is we wanted to ask the questions, what do business journals publish, not in one year, not in one journal, but across all the journals, across all the fields, over all the years that these journals existed. Yeah, so we picked 3 different fields: information systems, management, and accounting, 3 business disciplines. And the top journals in each of them. You can see them on the right-hand side. And we took every journal paper ever published over the years of existence. Yeah, from 1977, some of them, to 2001. We did this study in around 2007 or 8, right? So we had to stop somewhere. And you see on the right-hand side that we now had 8,500 papers, basically, right? Now, can this be done manually? Sure, if you have a few years of time to read 8,000 manuscripts, you can do everything that we've done to understand what these journals published manually. But of course, through LexiMancer, to such a tool, this is becoming, like an activity you can do within a few hours, so to speak, right? So we wanted to analyze, what do these journals publish individually, over time, and in comparison to one another. Yeah. So for example, this is a topic map of the themes, the research teams that IS journals published at the very beginning. So in the late 70s, when this field was incepted and these journals came into being, right? And you can see here that apparently you had topics such as systems analysis, you had things like organizational performance through IT, you had the relationship between systems and jobs, and you also had, information in accounting, because one of the key reasons here is that information systems in the beginning were used for accounting purposes, right? So here we see that these topics were basically a high-level view, a very abstract view of what the journals published in information systems 50 years ago. You can then, of course, study how does that look like over time in a different period of time. So, example, in the late 90s, in the early 2000s, what did we publish then? And you can see here that it moves away from systems analysis. You don't see this concept map, these concepts appearing on the map very much. Instead, we now have a lot more firm performance, business development, strategic issues. So it moved a lot more from how do we build, analyze, and design systems, and what does it do to our jobs, to now what does it do to the strategy and the performance of firms. So we basically moved up a level, so to speak. Yeah. So what is the implication of systems to markets and so forth? And so you see here that these themes shift with time as some issues are either solved or become more pressing over time. What you can also do then, with the help of such a tool, is you can have a look at, when you build these topic maps over time for each of the fields, you can then have a look at whether or not, when you do this for multiple fields, say systems in accounting or systems in management or management in accounting, whether or not these drift in these topic areas, the way that these topics areas shift over time, say from systems analysis to firm performance. Yeah, and you think of what, of course, we did this for all the different time periods, for all the different journals. And then you can have a look at whether or not these drifts move in the same direction between the fields. Yeah, and this is what you see here. Yeah, for example, when you look at accounting and information system versus management, right? You see here, that's the bottom chart. You see here that information systems and management, in a way, moved in a similar direction. They sort of follow the same way, but information systems and accounting, top left, you see that they move further apart. Like the distance between these topics is further, while management came closer to IS. Yeah, and if you know a little bit about the field, you see that information systems accounting were very early on, because, as I said, information systems were sort of used for accounting purposes recording and accounting and monitoring purposes early on. That was the main purpose we had information systems in the 70s. And then they became more of a management tool, right? A firm, a strategic asset in the organization over time. And this is what you see here, that the field of accounting and the field of information system move away, but the field of management and information system grew closer to the fact that they're sort of almost overlapping by now. Yeah, and this is something that you can see here in these topic maps that you can identify algorithmically. For example, here we're condensing all these latent, like the content into points on a map. Yeah, and then we can measure the distance, quantitatively measure the distance between 2 points. And the points, remember, are collections of actual topics, yeah, actual words and themes that are being discussed. Now, again, all of this is possible to do manually, but over a 40-year time period, over 8,000 papers from, all these journals, this is very, very difficult. And of course, also, these sort of precise measurements of the topics and the distance and the drift in mathematical terms, again, is very difficult to do manually. But of course, with such a tool, it allows you to sort of quantify some of these relationships that you can think of. And this is a good example for augmentation. Finally, I wanted to give you an example for computational automation. Remember, these are tools that carry out certain steps of the research process with little to no human intervention. So autonomous algorithmic computation of either data that is generated or the analysis of data. This example is not from me, but it's actually from an alumni from the University of Hamburg, Jan Hartmann, who is now professor at the Technical University of Munich. And I found this piece of work very impressive. That's why I'm showing you. What he's trying to do, he's a marketing professor, and what he's interested in is basically influencer marketing on channels such as TikTok and Instagram. Now, TikTok, Instagram, as you would know, are online digital media channels where you not only have text, but you also have videos and imagery, right? So you have what's called multimodal content in a variety of formats: text, numbers, audio, video, pictures. Yeah. And of course, as a marketing scholars, people want to see is whether a piece of marketing content ultimately leads to people being interested in whatever is being advertised. And then, of course, being converted, like whether they actually end up buying it, right? This is the so-called the purchase funnel. Like you see an advertisement, then do you go to the web page where you can buy it? Yeah, to the landing page. And do you then actually go and buy it ultimately, right? So this process, the purchase funnel, which has multimodal content. And the question that they're interested in is, how important is it that across these different steps of the purchase funnel, where you have content in different formats, maybe from a TikTok video to a text-based web page to an actual, Amazon page where you pay money quantitatively, right? Whether this content, does it have to be coherent? Does it have to be consistent? Or can I do something really whacked and different in one of these channels? Now, what they've done is they've done this for not just one ad on one page for one item that you can buy on Amazon, but they've done it for products across 20 categories: beauties, cars, fashions, for over 100,000 observations, so pairs of images and text. Yeah. So, Instagram images where you can click on, go to the landing page, and ultimately end up buying it, right? Over a period of about 9 months in the US. And they have dependent variables, which are click-through rates, which is the rate of someone watching the video or the image, clicking on the landing page, and then going to the online commerce site. And conversion is then whether or not actually someone ended up buying it. Now, the question is, if you want to identify whether the image that you see on Instagram and the text on the landing page and the product description on the commerce page, whether they are the same, whether they are coherent, you need to find a way of making all of these comparable, right? And if you have over hundreds of thousands of pages over 9 months across products in 20 categories, you have to find a way of doing this automatically. You can't manually do this. Yeah, so here's an example of how they've done this. They've taken an advertisement like the image, the image you see here, where someone cuts a piece of fruit, yeah, a piece of vegetable, and you have like a captioning, like a teaser headline below that. That Dr. Becker can throw out this vegetable now. So first of all, you have image and text. The first thing that they've done is they're taking the text, the caption, and they did what's called a sentiment analysis, an algorithm that classifies text into a range of different emotions. What do we see? What does this statement express? Disgust, anger, a little bit of joy, sadness, surprise, right? So multiple emotions, and you can basically compute sort of how strong these emotions appear in the text. You can see here the strongest emotion here is disgust. I beg Americans to throw out this vegetable. Bleh! Right? Disgust, and not a lot of joy, as you can see, 001. And this is a way for you to automatically extract a particular emotion that is trying to be evoked by a statement. That gives you an analysis of the text. Now, you also need an analysis of the image, right? And here you have certain algorithms that allow you to inspect image and classify them alongside a number of dimensions. For example, one of the things they did is they've taken all of the images and classified them in either abstract images, like models and diagrams, or logos, these sorts of things, or concrete images, like pictures of real things, like a watch or a car, right? You can do this. And of course, you can try to automatically extract the sort of like the content of an image. You can see that here. You see that there is a picture of what appears to be an ice cream bar. You can now use a semantic extraction algorithm that tries to describe what is being seen in this image. This is the same sort of algorithm that you can see under Google Images, for example. We either give an image and tell me what do you see here, or you type in a keyword and it finds images that match that keyword, right? That's the same idea. Right here, for example, you see here that an image extraction classification algorithm would say that this image is about food, dairy, ice cream container, gelato, plastic dessert. And of course, you have a caption underneath, right? Get back to enjoying frozen desserts, etc. So you have basically what you're doing is you're converting images and text into two pieces of text. Yeah. One, the keyword describe the image, and one that the actual caption of the text. Then you can use an algorithm that computes the similarity between two different pieces of text. Yeah, and it asks like how similar is the description of the image with a caption underneath the image. So in this particular case, you see here that there is a similarity measure of 0.58, like almost 60% similar. It's somewhat similar, as you can see, right? Ice cream is there, frozen, lactose is dairy, and there's a little bit of similarity, but also not fully similar. Yeah. So here's another example of that. You can see there's tags that you create for every image, and there's title captions for every image. And then you can see how similar are these tags with the captions, right? So the fastest Air Force planes in the sky, and the tags for the image were outdoor sky plane, flying jet, airplane. That's a pretty hot measure of similarity, 65, almost 66 degrees. Now that we've done this, now that we've found algorithmic tools to measure similarity and sort of certain attributes of both images and text and so forth, now, of course, I have a bunch of numbers, right? And all these numbers I can now put into a particular regression and compare them with my dependent variables, like my click-through rate, whether people click on the Instagram ad, go to the landing page, go to the e-commerce site, and of course, what they actually end up buying and how much money they spend on this, right? And that allows you now to see something like, look, you see two different curves, basically. For the click-through rate, coherence is negatively U-shaped, meaning that less coherence to a certain point, more coherence to a certain point is bad for click-through. And if you have, at some points it sort of tilts. But for the conversion rate, for people actually spending money, more coherence is better up to a certain point. So it's a positively shaped U-shaped curve. So this is interesting because it says, look, depending on what you want do you want people to come to your landing page? Then you want less coherence. You want people to actually, buy what they see? Then you want more coherence. Now, all of that, again, remember, this is being done for hundreds of thousands of product pairs, lots of categories, a long time period, lots of social media users and actually consumers in a fully automated way. So they run a couple of scripts that allow you to like categorize these images, categorize the tags, extract the meaning of the text, extract the meaning of the image, compare these two, and relate them to the variables. Basically, one long script that automatically compares that for you. That's a very, very nice example of computational automation. Now, these are the three examples that I've picked, and they're kind of open now in a way, right? So this part of computational methods, especially computational automation methods, it's blooming. Like every month you see a new paper coming out with a new computational method, especially in automation methods. We've now seen computational automation method, machine learning methods for personality extraction, for things that allow you to identify my personality traits based on a piece of text that I've given you, or based on my tweets, or based on my LinkedIn post, or whatever else. Yeah. So we've seen other types of tools that allow us to measure all sorts of things about humans, about artifacts, about content, about videos. And now with all these automation tools, we can now use them in our research process. So in summing up, let's look at the advantages and challenges of computational methods. Advantages, and that should be clear by now. What we can do with the computational methods is we can substantially expand reach and scope of research, right? We can do things that are otherwise would manually be next to impossible or very infeasible or very resource consuming to complete. We can look at more content, more people, more papers, more everything, more data, right? Because these tools allow us to take over some of that aspect. It can also be faster, right? If we have an algorithm carrying out some of the work, an algorithm like Leximensa reads a book in a second, right? If you read Romeo and Juliet, you'll probably need a few hours or days for that. And of course, also because these are computational tools that always carry out the same algorithm in a way, they can increase the reproducibility and analysis and help reduce human biases in otherwise manually carried out tasks. They don't automatically do this. For example, Leximensa is a probabilistic algorithm, meaning that if you put in the same text, Romeo and Juliet, into this, it gives you a concept map, and next time it'll give you a somewhat different concept map. So they're not fully reproducible. Yeah, they're not fully replicable. But of course, for example, if you think about the algorithms that Jochen Hartmann is using for his coherence study, these are deterministic, right? So you do them over again, you always get the same results. What are challenges? Challenges is that this is a very much a new and emerging line of research in information systems and otherwise. What that always means is that we have very few guidelines available for how to carry out such research. There have now in the last year been the first couple of editorials and commentaries that tell us how to carry out such research, how to make sure it's rigorous, right, valid and reliable and so forth, or even how to evaluate such research. Right? But so far, there's fewer of these guidelines and benchmarks available, let's say, than for design research, for qualitative research or quantitative research. Also, there are, and we talked about some of these, there are validity threats, for example, from the digital trace data, right? Digital trace data is not normal research data. It's organic, it's not designed, and it has a number of other types of challenges like opacity. And of course, many of these algorithms are probabilistic, not deterministic, meaning that they themselves have challenges. And sometimes you may not even know or understand or have full transparency and explainability about how the algorithm actually works. Leximensa is one of these examples. Leximensa is a commercial tool. We paid for it, and we wanted to use it for research, and we were not allowed to see inside of the algorithm because that's commercial property, right? Some R packages, open source packages are easier. Like, for example, the ones that Jochen Hartmann is using, all of these are inspectable and transparent. All of these are open source, but the Leximensas are not. This gives you a brief introduction to computational methods, certainly an up-and-coming and very exciting genre of research in information systems, and this is just a very brief introduction. Thank you for watching, and thank you for listening.